Hello everyone, this is Tipu Sultan. In this presentation, I'm going to talk about JFET. So let's begin with the characteristic of JFET. As we know that there is a two kind of JFET. One is N-channel JFET and another one is P-channel JFET. So in this PPT, in this slide, I'm showing here two symbolic representation of N-channel JFET and P-channel JFET. So now the question is, how can we understand which one is N-channel JFET and which one is P-channel JFET? It is very easy to understand the which one is N and which one is P-channel JFET. We only need to focus on the arrow sign here. If arrow sign is toward the drain and source, then it is called N-channel JFET. And if arrow sign is opposite to the drain and source, then it is called P-channel JFET. So in here, D represent is gate, D represent is drain, and S is representing as a source. So now let's move on the next slide. So as I already told that there is a two kind of JFET. One is N channel and another one is P channel. So now let's begin with the N channel JFET. If we understand the N channel JFET, we also can understand P channel JFET very easily, because there is only difference between N type materials and P type materials. So let's begin with N channel JFET. So as we can see here that there is three reasons. One is P, another one is N, another one is P. So let's talk about a little bit about transistor. If we understand transistor, then we can understand JFET very easily. So in transistor, we know that there is like PNP transistor or NPN transistor. So we can see that there is two depletion region and three materials, right? So in here also three materials. There is a P materials, N materials, and also P materials. So by using three materials, there is two depletion region is occurred. So if I define the N channel JFET, we can say that N type materials between embedded P type materials to form two PNP junction. So if I talk about also N channel JFET, only the difference is in the middle region. If in this region is P type, then it is P type materials. If in this middle region is N type, then it is N type or N channel JFET. And if it is N, then it will be N channel JFET. So let's go to our previous slide, and I'll discuss more here. So currently in here, we have to understand first the depletion region. I already discussed there is a two depletion region. So if our depletion region is increased, actually what will happen? So in transistor also, when our depletion region, this two depletion region is increased, the N region decrease, right? Same thing is here. If our this depletion region is increased, this depletion region is increased, our N region will be decreased. So when our N region will be decreased, what will happen? There is lots of free electron in N region, right? There is lots of free electron. So if N region is decreased, the free electron number of free electron also decrease, right? That means our current also will be decreased, right? So there is the current is ID, drain current. So when our depletion region is increased, our ID current will be decreased. So this is one of the main point we have to understand here. Now, suppose there is a gate and there is a source. If we add here one voltage source between gate and source, as we know that if we want to change the depletion region, we need to supply some voltage, right? we saw in the transistor how we apply the voltage. Same thing is in JFET as well. If we want to change the depletion region, we have to apply the voltage. In transistor, there is two kind of voltage source. In the JFET also same thing. We have to apply two kind of voltage between gate and source, and also drain to source. So now at first I'll talk about gate and source. So in here, if we apply voltage BGS, so now what will happen? It will understand. We will understand now these things. So when the active region is decreased due to the BGS or voltage in gate and source, if we increase the voltage here, suppose our depletion region is decreased. So when depletion region is decreased, that means that our ID current is also decreased. So if our ID current is decreased, that means we'll get less current in drain, right? So in here we can say two things. One is to depletion region is proportional to BGS. How? Because depletion region width is totally depend on the BGS. If we change the BGS, our depletion region also will change. So that's why we can say that the depletion region is proportional to the BGS. And also one more thing, we can say that it is also proportional to drain current, because we know that if depletion region is increased, ID also decrease. If depletion region is less, ID current also more. So that's why it is proportional to also ID. To understand the JFET, let me give you an example. So before giving you an example, let me erase all the things here. So let's assume that we have one water tank here, and we connect our water tank with one bulb, and there is one sink here. So whatever water in the tank, this is called tank. So this water will flow through the pipe, and it will be here in the sink. And this water flow we can control by this bulb. Now this we can see, we can compare this sink with our drain, because all the water will come through the pipe, and it will be in sink. So we can say that sink equal to drain, and bulb, there is one bulb, right? So we can say that bulb equal to gate. Okay, gate. And in here the current is flowing, right? In here current is flowing from end region. So in here water is flowing. So we can say that water equal to current. Sorry, CEO. Current. Okay, this is the current. So in order to understand the working principle of n-channel JFET, there is two cases we have to consider. So first case, what? In the first case, we'll assume that BGS equal to 0. Now the question is, what is BGS? As I already discussed that there is three channel. One is gate, another one is source, another one is drain. So when we connect one voltage source between gate and source, that is BGS. So in the first case, we assume that BGS equal to 0 volt. And when BGS equal to 0, and what will happen in our in our JFET, in our circuit. Actually, when BGS equal to 0, uh, that means there is no effect on the end region. That means the drain current should be huge, or drain current should be more. And in the second case, we'll take BGS is less than 0. That means in the first case we take BGS equal to 0. Now in the second case we are talking about BGS should be less than 0. That means it should be minus like minus 2 volt, minus 3 volt, or minus 1 volt. It should be like that. But in both cases, one thing is common, that is BDS should be positive. It should be always positive. What is BDS? We have to understand these things also. So when we'll connect one voltage source between drain and source, that is called BDS. So we can also call it also BDD. Both are same. BDS and BDD both are same. So what I said, I'm going to explain again here. First case is BGS should be 0, and second case BGS less than 0. In both case, the BDS should be positive. So based on this condition, I will explain more. In case 1, BGS equal to 0. So but our BDS should be positive. So we can write BDS or BDD both same, as I told. So let's take BDS or BDD equal to 2 volt or 3 volt. It should be positive. So before discussing that, I am removing all the things from here, then it will be easy to discuss. So when we apply here, we say that in the first case that our gate and source voltage should be BGS equal to 0 volt. Okay, 0 volt. But our drain and source voltage, it should be positive. That means BDS equal to some positive volts. So just take 2 volt. Okay. So when we give 2 volt in first case here, what will happen in here? We have to understand. So when we give 2 volt here and we take this terminal positive and this terminal, it should be negative. When this terminal is positive, why this terminal is negative, we'll understand now. Because in this region we are using N type of materials. So it's all about the electrons. Electrons is negative charge, right? So when we use the positive terminal here, the electron will attract by the positive terminal, and this electron will flow in this way, right? Then there will be current flow. And there is also negative charge. So what will happen? Negative charge always repel each other, right? So it will push this electron in this way, and it will go in the drain to the source. So it will always flow in this way. Okay, I think it's very clear now. So in here, one more thing we have to understand, that there is a two kind of current flow. One is conventional, another one is normal. So which one is conventional and which one is normal? Today we will be very clear about it. The electron flow is in which direction? That is the normal current flow. That means electron is flowing in this direction, right, toward the drain. So this is the normal current flow direction. So opposite to the normal current flow direction is the conventional current flow direction. Okay, I think it is now it's very clear. Okay, let's move on to the next slide. it is just a p channel JFET. So whatever is happening in the n channel JFET, same thing is happening in p channel JFET. So in here only difference is p type materials. We use p type materials. Instead of electron, there is a holes. So in here, now we will try to understand actually the first case and second case. So in here we can see that BGS, this source, BGS, it is 0 volt, right? 0 volt, and BDD, it should be greater than 0. That means it always should be positive. Some positive voltage it should be here. So when we apply the positive voltage here and BGS equal to 0, there is not only flow the electron flow in this direction, not only that, but also there is something happening in the depletion region, right? When we apply the voltage, there is something happening in the depletion region, because it is a reverse bias condition, right? The depletion region is the reverse bias condition. So when BDD is increase, the depletion, it will also keep some effect in the depletion region, and depletion region also increase. So now we can see in this picture that in the upper region is more bigger than the lower region. So we'll understand why it is happening. So when let me first draw here. The region is like this, right? The upper region is more bigger than lower region. So why it is happening? So let me describe this one first. So to understand this one, we'll take the n region first. So suppose this is the n region, okay? So suppose it is one materials. So we know that every materials have some resistance, right? Every materials, even its copper, there is also some resistance. So there is also some resistance, right, in this material. So instead of considering the resistance, we take some resistor. It's same, right? So we are taking 4 resistor here. So suppose R1, R2, R3, and R4. So if there is 4 resistor and it connects, suppose in here it is connected with this wire, right? So same thing, we'll connect these materials with the voltage source. So in here it is BDD or BDS, okay, and it should be positive voltage. So suppose we will give 2 volt, positive 2 volt. So when all the resistor is connected in series, so what is the equivalent of Req equal to, it should be R1 plus R2 plus R3 plus R4, right? R1 plus R2 plus R3 plus R4. So it will be the we'll just add up all the resistor together if it is in the series. Okay, so we already know our voltage is kato. Our voltage is 2 volt, right? And our total resistance, suppose R1 is 2 ohm and R2 also 2 ohm. All the resistors value is 2 ohm. So that means our R equivalent should be 8 ohm, right? So BDD is 2 and R equivalent is 8 ohm. Then from here we can find out our current, right? So that means I equal to B by R. So in here B is BDD or BDS, that is 2 volt and R is 8. So from here we can find out that our current is 0.25, okay, 0.25 ampere. So we know the current. So from the current we can understand how many voltages are disappearing in every resistor. We can easily, so for R1, suppose for R1, how we will find out the how much voltage is dropped between the R1. So let's B1 equal to B equal IR, right? So I is 0.25 into R is 2 ohm, right? So from here we can find out 0.5. That means 0.5 volt is disappearing between R1. So same thing, when R1 is, if we apply 2 volt here, then in here it should be 1.5 volt in R1, and in here it should be like a 1, in here it should be 0.5, and in here it will be 0. So that means 0.5, every resistor will drop 0.5 volt. So if there is four resistor, then every resistor, when it drops 0.5 volt, that means in the last, after the last resistor there is 0 volt, right? So from here what we can see, how from here we can see that there is 1.5 volt, right? There is 1 volt, there is 0.5 volt, okay, and there is 0 volt. So same thing is here, same thing is happening in this region. So if in here there is one resistor, there is one, there is one, there is one, there's 4 resistor. So in here we can see that there is 1.5 volt. So voltage is big, right? When voltage is bigger here, that means there is the reverse biasing voltage is big and the depletion region should be big, right? So that's why in the upper part is more bigger than in the lower part. I think it's very clear now. Okay, now let's move on to the next slide. So in here we'll understand the pinch of voltage. So in reverse bias condition, what we learned before that, when in the transistor like PNP transistor, when we increase the reverse voltage, so what is happening? The depletion region is increase and increase. But in the certain time, when we increase more voltage, there is a breakdown is happening, right? Or depletion region also increase more. So in here not breakdown is happening, but when we increase more BD voltage, or sorry, BDD or DS voltage, BDS voltage. So in that time, the upper region is more increase and more increase due to the reverse bias, right? So when the voltage is increased in certain level, then both region will meet in one point. So when it meet in one point, that is called pinch of voltage. I think it's very clear. I'm explaining one more, that when we increase the BDD or BDS voltage in a certain level, a certain time, the both depletion region will connect together. So in that time, when it connect together, that is called pinch of voltage. Now let's take again we'll talk about in two cases. In first case, suppose BGS equal to 0 volt. In that time, BDD should greater than 0 volt. Okay. In the second case, BGS it should be less than 0 volt, and also BDD prime should be less than BDD. Now the confusion, right? There is BDD. What is BDD prime? It is nothing. It's both are same. Like, we only try to differentiate both of them. Suppose if in here we apply 2 volt BDD, in here the BDD prime should be less than BDD. So that means it should be less than 2 volt. Okay, I think it's very clear. Now I'll describe about output characteristics of JFET. So it is the main point of this discussion. Um, to understand the output characteristic of JFET, we have to know that ID is the output current, and BDS. In here we see this, see that BDS is the output voltage. So BDS, it is totally independent, and ID is dependent, dependent variable. Whenever we explain about n channel JFET, we'll take BGS in negative. Like sometimes we will take BGS equal to 0, and sometimes we will take BGS -1, -2, -3, -4, like that. Will not take any value BGS positive value. Okay, we will always take the negative value, and BDS will be always positive. We can see here that it always positive, right? Okay. As we know that we can control depletion layer by two ways. One is by controlling the BDD. One is controlling by BDD. Previous slide we see that here, that we can control the depletion region by BDD, or controlling the voltage of BGS. Now in here BDD is in here we can see that BDS or BDD is in x-axis, and also ID is in y-axis. So see that what happen if BGS equal to 0. See, this is the first case. Okay, this is the first case. When BGS equal to 0, what is happening? What is happening in our in the circuit? So to understand that, I'm going to this circuit, and let me clear all the things here, then it will be easy to understand. So I'm already clean up everything. So now in the first case, what I have taken, BGS equal to 0, and BDD should be some positive volt. So when we give some positive voltage in BDD and BGS equal to 0, the depletion region, when we increase the BDD, the current depletion region also increase, and current also flow in this direction, right? When depletion region is increasing, in some point it will meet, and that is called pin joint, right? So what happened here? See, the current before when we apply the 0 volt in BGS, and also we increasing the BDS voltage, so current is flowing in exponentially. Current is flowing in the exponentially in this region. Okay, in this region current is flowing exponentially. When we increase more BDD voltage, and it meet in this point, right? In this point it meets. So when it meets, so then there is it's like block, right? Block the area. Now no, there is nothing happen, right? No current is flowing, no ID current here, right? So in that time what happens? See, it's saturated. See, the output is saturated. There is no output current, right? Now let's take that BGS equal to -1. That means, again I'm come back to the previous slide. Now we are taking that this voltage is -1. BGS equal to -1. So now when BGS is equal to -1, also BDD equal to positive voltage. Now what happened? See, in the previous time BGS equal to 0, but BDD only the voltage. So that's why it takes long time to meet together, right? These two regions in here, these two regions meet together, it takes time. Now when we give 2 voltage, so for 2 voltage, the two region will meet too fast, right? Like better than first one, right? So that's why we can see that the in here in this diagram, when we give minus 1 volt, the pin joint, see in here there is a pin joint voltage is here, right? In here the pin joint voltage, sorry, bp is more faster than first one, right? Because we apply bgs, okay, minus 1 volt. Now see, if we increase bgs minus 1 to minus 2 volt, our pin joint voltage is more less, right? Pin joint, that means our uh, uh, what to say, our pinch of voltage, our pinch of voltage is more faster, like it takes only few times to combine, right? If we increase the bgs again and again, minus 2, minus 3 volt, minus 4 volt, that means, and also increase the bdd, that means our pins of voltage is decreasing. That means we need very less pins of voltage, or that means within very less time our two depletion region will be connected together. So that is the reason. Okay, that is the reason behind the bgs. When we applying bgs in minus voltage, this thing is happening in the circuit. I think it's very clear now. I'm again explain in briefly, like when BGS equal to 0, we apply BDD, right? When BDD we apply, it takes long time to connect two depletion region together. So that's why our pinch of voltage is higher. When we apply both voltages like BGS and BDD, in that time our pinch of voltage is less because it getting faster. The depletion region is connected together faster than first case. So that's why the pinch of voltage is decreasing. Okay. And also we understand why it is saturated, because when it's meet to the pinch of voltage or pinch of voltage, or it meet together the two depletion region, then there is no electricity is flowing, right? Okay. So now we understand previously that in the transistor or in the diode, when we apply reverse bias voltage more and more, sometimes when we extend more voltage in some extent, there is a breakdown happen, right? Same thing is here as well. When we apply more bgs minus negative voltage and bdd, in that time, if we limit the cross of our reverse bias voltage, then there will be breakdown. Then the current again flow exponentially. It will increase exponentially. So that is called breakdown region. See, in here we already write down, this is the breakdown region. Okay. And this region is called ohmic region. Now the question is why it is ohmic region. What we know, ID current or drain current is proportional to what? BDS, right? Drain source voltage. So that's why we can say that it is the ohmic region. Okay. So from here, from this in this slide, I already discussed about the characteristic of JFET. So that is all for today. Thank you so much for watching.